Hello and welcome back to Basic Topology, the video series where we talk about how we can use topological spaces in analysis. And indeed, in today's part 11, we will talk about a very important result for continuous functions known as Urysohn's lemma. This one gives the foundation for something we call partition of unity, and I will use that in a lot of other videos. However, as always, before I explain what this exactly means, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And moreover, as a supporter, you can use the link in the description to download additional material for all the videos. And then without further ado, let's immediately sketch a topological space X. In fact, now we want to restrict ourselves to locally compact Hausdorff spaces. This is one possibility for the formulation of Urysohn's lemma, but even that can be generalized. But for us this is already good enough because important spaces like Rn are already covered with that. And now there's a reason why I sketched this topological space as a line, because I want to show you a graph of a function. This means now we consider a map from X to R. And now I can already tell you the important part is that the function is equal to 1 at a given region. Actually, we can make this really precise because we have a compact set in X, and on this compact set the function should be equal to 1. So maybe a common name for a compact set could be K. Hence here in the picture the graph of the function we are interested in is just a constant over this compact set K. And now in addition to the compact set K, we also have a larger set U, which is open and contains K. In fact, this is the second ingredient, so I just give you two sets, one compact and one open. So let's call the open set U, and now we want that the function is 0 outside of this open set U. Obviously in the picture this is not a problem at all, we just set it to 0 here and there. However, now the thing is that we actually want to have a continuous function, so we have to connect all the pieces continuously. This means from 1 we have to go down and we have to reach 0 before U ends. In fact, we want to have a little bit more, namely that the whole support of the function lies in a compact set as well. So we have two things you can remember now. On the one hand we want to have a continuous function, and on the other hand we want to have one with compact support. So you definitely already know what continuous means, but maybe you are not so sure what support actually stands for. Therefore, before we formulate our theorem, we should first clear up this in a definition. And for that we don't need much structure, it's sufficient to have a topological space and a continuous function. And when I say the word function, I actually just mean a map from X into R. But we also often allow for complex valued functions, which means that we would map into C. But no matter if we consider R or C, both just carry their standard topology. Indeed, the topology is important if we talk about continuous functions. However, to define the support we don't need any continuity yet, so it just works for any function from X into R or X into C. So we just consider all the points X in X, and then we look what the function f does with them. More concretely, if we don't map X to 0, then we put it to the support of f. But this is not all, because we also form the closure of this set in X. So you can already remember, by definition the support is always a closed set in the topological space X. And indeed there's also a short notation for this support, which you might see a lot. It's quite simple, support of f just stands for this closed set in our topological space X. And now we can use this notation to define a whole vector space, which is denoted by capital C with index C. The one C stands for continuous and the other one for compact. And as already mentioned, this stands for vector space consisting of functions. And then as before, it depends a little bit on context if you want a real vector space or a complex one. But for a definition here it does not make any difference because we want to have the continuous functions that have compact support. So we only consider the functions here where the closed set from before is actually a compact set in X. And that this set actually defines a real or a complex vector space is not so hard to show. Okay, so now we have everything we need. We have the support of a function and the continuous functions with compact support. Therefore, the next step is just the formulation of Urysohn's lemma. It's called a lemma because there is a nice generalization of this result, which can be proven by using Urysohn's lemma. But as already mentioned, we don't care so much about the extensions right now, because we just want to formulate it in a locally compact Hausdorff space. Simply because there we can already do a lot and it's sufficient for our applications. And now, as we have done it in the picture before, we just fix two sets, an open one and a compact one from the space X. And as before, let's call the open set U and the closed set K. So these are the assumptions we have, and then we find a nice continuous function with compact support. And now we can just list the properties we have already stated in the picture before. So as a reminder, I put the picture here, and then we can actually formulate three properties. So first, all the values of f should lie between 0 and 1. So this is exactly how we have it in the picture, which means there's nothing going on above 1 and nothing going on below 0. However, we want even more, because we want that the function vanishes outside of the set U. And now we have a nice way to describe that, because we can just say that the support of f lies completely in U. Indeed, this means that all the points where the function is non-zero lie in U. And then finally, the last property should tell us that the function is exactly equal to 1 on the compact set K. And this we can simply write as f restricted to K is equal to 1. And there we have it. These are the three properties for the function f that Urysohn's lemma gives us. And sometimes it's also good to rewrite these properties in a short way by using the indicator function, which we have discussed in part 9. So in short, we can just say there exists a function f that is continuous and has compact support, and it satisfies that for all points in the domain we have an inequality. And this inequality we can just formulate with indicator functions. So I write chi for the set K on the left hand side and chi for the set U on the right hand side. And now these two indicator functions, also called characteristic functions, can be visualized in the graph as well. So first, chi k is the indicator function that is 1 here and 0 as well. And therefore our function f here always lies above this characteristic function or is equal to it. This means we can just write less or equal than f of x. And on the other hand, the second characteristic function is 1 on the whole set U and otherwise 0. Which also tells us that it always lies above this function f or is equal to it. So in summary, we can just say that the two inequalities here are equivalent to the three properties from before. And moreover, it also tells us that the function f is fixed at most points, because there's only some freedom here in the transition zone. And please never forget, this connection from top to bottom has to happen in a continuous way. That and the compact support is the only additional thing we require here. And I would say here, if you read Urysohn's lemma like that, you might already believe it, because it really sounds intuitive. Indeed, it should just be possible to increase the function f continuously from 0 to 1. However, to actually do that in this general context requires some work, and this is what we will do in the next videos. And you will see, by formulating the proof, we will also show some general statements that hold in locally compact Hausdorff spaces. Therefore, I really hope that we can do that together in the next videos and that we meet there again. So have a nice day and bye bye.